Hey everyone, welcome. Today we're diving straight into the cosmos for this explainer. We're going to borrow some incredible insights from physicist Brian Cox to basically unpack the entire universe, our place in it, and, well, where the whole thing is heading. Let's get right into it.
This quote honestly hits the nail on the head. Cosmology is terrifying, right? When you start peeling back the layers of space and time, it forces these really vivid, deeply human questions about what on Earth we're actually doing here. Whether you're a quantum physicist or just staring up at the night sky, we all wonder, how did I get here? What's our future? What was our past? So we're going to feed that natural curiosity today.
Just so we don't get totally lost in the vastness of space, here is our roadmap. Number 1, the cosmic scale. Number 2, origins and the multiverse. 3, the dark universe. 4, inside a black hole. And 5, life and our future.
All right, kicking things off with Section 1, the cosmic scale. Where are we? Because, honestly, before we can figure out what we're doing here, we really need to establish just how brain-numbingly huge here actually is.
200 billion. That is the estimated number of stars just in our local neighborhood, the Milky Way galaxy. And modern astronomy tells us almost all of these stars have planetary systems. Out of those, we're looking at around 20 billion potentially Earth-like, rocky planets orbiting at that perfect distance from their star to support liquid water. 20 billion. And that is literally just in our own galaxy. So yeah, the Milky Way is incredibly crowded, but it's also unfathomably massive. It's 100,000 light-years across. To put that into perspective, say you wanted to leave our galaxy and just wave hello to someone in our closest neighbor, Andromeda. Well, Andromeda is over 2 million light-years away, meaning if you sent a message traveling at the actual speed of light, it would take 2 million years to get there and another 2 million years to get a reply. A 4 million-year round trip, just to text your closest cosmic neighbor.
And if your brain isn't completely numb yet, let's zoom out to the broader universe. 2 trillion. That's the estimated number of galaxies in the observable universe. 2,000 billion galaxies, each packed with hundreds of billions of stars, stretching across a chunk of space that's 13.8 billion years old. And remember, that's just the bubble we can actually see.
Which brings us to Section 2, Origins and the Multiverse. Where did we come from? How did all of this unimaginable scale even come to exist in the first place?
So our universe as we know it kicked off 13.8 billion years ago. But the accepted theory isn't just a simple explosion. Before the universe was this hot, dense soup, it went through a phase called cosmic inflation. In a literal fraction of a second, we're talking 10 to the power of negative 37 seconds, the universe doubled in size incredibly fast. Then, that rapid expansion slammed the brakes, dumping all its energy into space, and boom, that creates the hot Big Bang. Fast forward about 380,000 years, and the universe finally cooled down enough for atoms to form, which meant light could finally escape. We can actually photograph that exact moment today. It's called the cosmic microwave background radiation. It's basically a baby picture of our universe.
But here's where it gets wild. That incredible period of inflation? Theorists think it probably didn't all stop at once. Picture an endlessly stretching fabric of space-time. But the stretching slows down and stops in these little isolated patches. Each patch that stops stretching and dumps its energy creates a Big Bang and a brand new universe. If this theory, known as eternal inflation, is correct, our universe is just one tiny bubble in an infinite, constantly growing fractal multiverse. That means literally every possible combination of the laws of physics might exist somewhere out there.
Section 3, the dark universe. What's hiding in the dark? Because with all those universes and trillions of galaxies, you'd think we have a pretty solid grip on what the universe is made of, right? Well, think about everything we just talked about. The 2 trillion galaxies, the stars, the planets, you, me, everything we can see and interact with makes up just 5% of the universe. Just 5%. The rest is entirely invisible to us. Roughly 25% is dark matter, and a massive 70% is dark energy.
Let's break these mysterious forces down real quick. Dark matter acts kind of like invisible cosmic glue. We know it has to be there because we can actually see its gravitational pull affecting how galaxies rotate, but it completely ignores light and normal matter. Dark energy, on the flip side, is doing the exact opposite. Discovered back in the late 90s, dark energy is this bizarre property of space itself that is actively pushing the universe apart. It's causing the expansion of the cosmos to actively accelerate. This is the absolute cutting edge of theoretical physics, and honestly, we still don't truly know what either of them are.
Speaking of things we don't quite understand, let's move to Section 4,
inside a black hole, pushing the edge of knowledge. These are the most extreme objects out there, formed when massive stars run out of nuclear fuel and just collapse completely under their own insane gravity.
Okay, let's say you decided to fall into a supermassive black hole. According to Einstein's general relativity, here's what happens. Step 1, you approach the event horizon. That's the point of no return. Step 2 is where it gets super weird. If I was watching you fall in, I would never actually see you cross the edge. Because that massive gravity curves space and time, your time would appear to slow down from my perspective. I just see your image freeze on the horizon and slowly fade to red. But for you, moving to step 3, you cross the horizon totally unnoticed. You wouldn't feel a bump, you'd just slip right through. Step 4, though, that's unavoidable. Once you're inside, you are pulled inexorably, unavoidably toward the center singularity, and there is absolutely nothing you can do to stop it.
But here's where we kind of have to practice some scientific humility. We simply don't know how to describe black holes properly. This is the absolute edge of human knowledge. Einstein's math brilliantly describes the event horizon and the outside of a black hole. But at the singularity itself, the math just breaks down into infinities. It stops working. We literally don't have the tools to describe it right now. We're going to need a future quantum theory of gravity, maybe string theory, to finally unlock what's truly happening inside.
All right, Section 5, Life and Our Future. Are we alone, and how does it end? We've explored the infinite multiverse and the crushing depths of black holes, so let's bring this massive cosmic scale all the way back down to us.
Compared to a 13.8 billion-year-old universe, humanity's story is just a brief, fleeting spark. 4 million years ago, our ancestors were essentially upright walking apes. But then, around 1.8 million years ago, rapid, extreme climate change in Africa's Rift Valley created this intense evolutionary pressure. The absolute need to adapt to violent environmental shifts drove an explosion in brain size and intelligence. Homo sapiens, us, we've only been around for a mere 200,000 years. That's a tiny, tiny fraction of a cosmic second.
Which brings us to a really fascinating cosmic puzzle known as the Fermi paradox. If there are 20 billion Earth-like planets just in the Milky Way, why haven't we seen any aliens? Where is everybody? Well, the evidence paints a pretty sobering picture. Life started super quickly on Earth about 3.8 billion years ago, but for over 3 billion of those years, it was nothing but simple single-celled organisms. It took a massive, unbelievable string of lucky accidents to eventually produce complex life, let alone a civilization that can actually go to space. So it's highly probable that while simple life might be everywhere, complex, intelligent life is extraordinarily rare.
And frankly, that rare intelligence is on a ticking clock. In about 5 billion years, our sun is going to run out of fuel. It'll swell up into a red giant, and the Earth will literally be roasted into a cinder. Now, long before that even happens, our planet will get too hot for complex life to survive. So if human civilization is going to endure, we have absolutely no choice but to expand out into the solar system, likely starting with Mars, since it has the water and resources we'd need to build a new frontier.
But what about the universe itself? Well, our best estimate right now is that dark energy is just going to keep pushing. The universe will continue to accelerate, doubling in size every 20 billion years. Eventually, the stars will burn out, the black holes will evaporate through Hawking radiation, and the whole universe will just fade into a cold, dark, eternally expanding state. The amazing complexity we see today, stars, planets, and us, it's really just a temporary phase in a beautifully decaying system. Which leaves us with this final provocative thought. If we live in a decaying universe, surrounded by trillions of silent galaxies, where our specific intelligence is just a highly improbable temporary accident, how incredibly valuable does that make us? It means we might be the only part of this vast cosmos that can actually look up, think, feel, and try to make sense of it all. And I think that makes our fragile little existence something truly worth celebrating. Thank you so much for joining me on this explainer today. Until next time, keep looking up and keep asking those terrifying, beautiful questions.